All right, hey. So we're gonna get into um, some more interesting uses now of autonomous kind of behavior. But before we do, we're gonna review the dot product because, as you've seen, the behaviors up until now have largely been in whatever direction. So if you have an object here and an object here, and they're trying to flee or seek or whatever, that could be in any particular direction. But usually in the world that we live in, there are other things in that environment, or you do want to take into consideration what an agent can see, and we've talked a little bit about that. So the dot product is a really powerful and very, very simple mathematical concept that can be used to really determine sort of direction, uh, and it's surprising how simple it is, and it's something that not only can we use for direction, but we also use for things like projections. So you've already seen this when we were talking a little bit about collision detection previously. So let's dive into it. Let's kind of review it, but you probably already know a lot of this stuff. So the dot product, one of its capabilities is to determine the angle between two vectors. It looks like a product, but it is an element-wise product, and it returns a single value. So unlike a matrix multiplication or something like that, or say multiplying a matrix by a vector or a vector by a matrix and so on, a dot product will just give you a value. And that value we can then use to determine the angles of things, of those two vectors. And if we know enough information about those vectors, we can determine whether or not something's in front of that vector or behind. And this is really, really useful for determining collisions and kind of the environmental information around you. So here's a couple of examples of what the dot product looks like for a variety of different sort of scenarios. So if two vectors are pointing in the exact same direction, you're guaranteed for that to be a positive number. If they're pointing in sort of opposite directions, or not exactly, it's going to be a negative number. And if they're perpendicular, then the dot product is going to be 0, which is also a very useful thing to know. And if you're thinking kind of trigonometry, you can kind of remember that in certain cases, for a particular function, a particular trigonometric function, the value of that trigonometric function when that value is perpendicular or 90 degrees is 0. And that value, that function, as you may recall, is the cosine. And we'll see kind of how that fits into this in a minute. And so just kind of thinking again, right, if, I forget this guy's name. I used to love this show, but whatever. Say I want to know, what to avoid, what's behind me, what's in front of me, how do I get to the donut, knowing that the dot product between my forward direction and the donut is positive means it's in front of me, whereas the ninja behind me, because it's negative. And that way, if I'm writing an application like a game and I want to kind of do know what's behind me, what the agent can see and what they can't see, versus and then knowing which direction to go, we can kind of figure out what to do. So the we can also use an alternative vector, so we don't actually have to use the forward vector all the time. So if you want to figure out if something's to your left or to your right, then we have a right vector, which is going to be perpendicular to our forward vector. So there's a number of ways to calculate that in 2D. It's very easy, it's just the reciprocal. In 3D, it's going to be a cross product, if for example. But if you have your right vector and your left vector, then you can figure out if something's to my left and to my right, and you can kind of create all those different behaviors. Ultimately, what this is doing is it's effectively creating a plane in space, or it's dividing space into two sides. And if you're on that plane, the dot product will be 0. If you're on either side, you're going to get a negative or a positive. So you can kind of imagine, as you get into deeper decision scenarios of like how to organize your scene, how to make decisions, and more complicated path mapping and so on, the dot product shows up a lot. So this is the kind of equation for the dot product utilizing the magnitude and the angle of separation between two vectors. And so this is actually really, really important. If your vectors are unit vectors, so if you've normalized those vectors, then you don't actually have to think about the magnitude at all, and all you have to care about is that angle. So at that point, the dot product is exactly equal to the cosine of the angle separating. And if you recall cosine, if they are equivalent, if the angle is 0, then the value is 1, and then it kind of goes to 0 at 90 degrees, and it goes to -1 at 180 degrees. Yes. To -1 180 degrees, and then back to 0 at 270, and then back to 1 at 0. So then if you do have vectors that are not normalized, then you can effectively use their magnitudes, which you can determine using the Pythagorean theorem, which we'll talk about in a second. If the angles are obtuse, meaning there is more than a 90-degree separation, you are guaranteed to have a negative value on the cosine. The magnitudes will always be positive, be it a unit vector or not, and so in that sense, this allows you to, if your dot product is greater than 0 or lesser than 0, you know if they're pointing in the same direction or not. And if it's equal to 0, then you know that they're perpendicular. Here's kind of an example that you can work through. In this case, A is the magnitude is 6.2 and B is 4.1, and they're separated with 15 degrees. And you can see that A dot B is going to be 24.4, and that means that it's a positive number, and it's clearly pointing in the same direction. Now, if you wanted to, right, you could get just the cosine by dividing that dot product by the product of 6.2 times 4.1. So if you were to move the A dot B divided by the product of the magnitudes, you would then be given the cosine of the theta. So say you don't know theta, but you know everything else, you know the dot product and you know the magnitudes, you can determine what the angle is, which we'll see in kind of the next method of determining the dot product. And so here you can kind of see that sort of running through, and we can figure out what the magnitudes are using the Pythagorean theorem, which you're probably pretty comfortable with at this point. Another thing you'll notice here is what's really powerful about the dot product is you can use it to effectively project the top vector onto the bottom vector. And this is something that's used in dot products a lot, where if you think about the triangle A to the B, that creates a little kind of mini triangle there. And you know that the cosine is going to be equal to that point to the radius. So if you were to rewrite cosine, and you know the dot product and all the magnitudes, you can actually determine what that component on B that A has. And to do that, you'd basically just take the magnitude of A, in this case, and multiply it over on the other side, because cosine theta is also equal to that component divided by the hypotenuse of this triangle. Right, so cosine is, is the adjacent. And so what you get then is basically the dot product divided by the magnitude of B is going to give you the component of A against B. And this is what's called a projection of the vector A onto the vector B. So this is actually not that valuable in context of collision detection and things that we're doing here, but you'll find this to be very, very valuable in many other places. For example, in the separation axis theorem, or other places where you want to determine if things are overlapping, which is pretty valuable. So this is the mathematical formula for the dot product that is sort of like the linear algebra version. Really, all the dot product is an element-wise sum of the two vectors. So when you have an A vector with two components x and y, and a B vector with x and y components, what you do is you multiply the two x's and you add them to the multiplication of the two y's. So you element-wise multiply, and then you sum everything up. And for the third dimension, you just do that with z. So it'd be x times x plus y times y plus z plus z. There's no normalization, there's no nothing. This is why the dot product is so powerful, because it's basically a bunch of multiplies and additions. And so you don't need to do trigonometric functions, which are relatively more expensive. You don't have to do any square roots, nothing. And from that, you can get a trigonometric function. So you can kind of see it's a bit of a shortcut and a performance speed up if you can utilize the dot product over other things, like a matrix multiplication, for example. So in this case, to use this example, right, we have an A 5-3, B is 8-0. We do that, and you can see that the dot product is going to be 40. If you were to plug this back into our previous equation, right, we could say, okay, well, 40 divided by the magnitudes of A and B would be equal to the cosine of theta. So if we take the inverse cosine of 40 divided by looks like 15 plus 64, or 79, so 40 over 79, let's do the calculation, right? 40 divided by 79, great. And if we can do I do not have inverse cosine, but maybe I have. Hold on. Okay, so if we're in Python, we have 40 divided by 79. Okay, 40 divided by 79. And if we do math.a cosine, which is the inverse cosine, great. So we get 1.039, which is 1.039 radians, which to convert it into degrees, we would do then times 180 divided by pi, I believe. And so it's 60 degrees is the angle between these two things, which makes sense, because if you think about B is just along the x-axis, right? And A is 5, but 3, so it's got a pretty intense slope, which is good. Cool. So that's kind of it for the dot product review. A lot of this stuff should be pretty familiar to you at this point. And again, like we were talking about, how this stuff is using the dot product can be a way to avoid utilizing a square root calculation, which can get expensive over time. So that way we can avoid that, especially if you're just trying to determine if something's in front or behind you. And the dot product can be doing that for you with just a few multiplications and additions. And so so if we use the magnitude squared, then we can avoid that square root calculation. I think I've talked about this subject before, right? Like if you can stay in the squared range, then that's better. And what's nice about if you kind of break down the dot product equation, and if you take everything to the power of 2, you can still kind of coexist in that squared world. But generally speaking, if you can avoid the square root, I think the point of this slide is to just kind of to indicate that just avoid the square root at all costs if you can. But computers today are pretty fast, so I wouldn't worry about it if you have to. Okay, so that's it for the dot product, and moving on to the next thing this week.